All right, welcome back. So this is our last topic here in Unit 5, the idea of optimization. So optimization is just simply using a real-world scenario. It doesn't necessarily have to be perfectly real-world, but something that's realistic-ish, and creating a function to model this situation. And as we've been discussing with both Unit 4 and then especially here Unit 5, we can find things like maximums and minimums depending upon the situation. Maybe we want to find the maximum profit of some sort of like cost revenue kind of situation, maybe a minimal cost, or maybe we want a maximum area, minimum or maximum volume of the minimum surface area for a three-dimensional shape, stuff like that. So we can do this by creating our function and then taking the derivative and saying the derivative equal to 0. That's how we find maximums and minimums. And then obviously we then do our first derivative or second derivative test to determine if it's truly a max or a min. So a couple strategies. When possible, drawing a picture is always useful. Identifying known and unknown quantities, what we're given, what we're looking for, things like that. We want then the equation that we want to optimize. Sometimes this is a single equation. Other times we're going to use what's called a primary and then secondary equation or equations. The primary equation is what needs to be optimized, and sometimes we need to use secondary equations to kind of feed into that. Because if our primary equation has more than one variable, we kind of need to get only one variable in the problem to make the derivative easier, so we want to use those secondary equations. And then we determine whether it's a max or min value with our calculus, derivative, and then first and second derivative tests. Using the endpoints to also verify that that could theoretically result in a max or min. So if we want the maximum amount, we don't necessarily want a relative max, we want an absolute max. So we do need to consider the endpoints. So we're going to take a look at, I've got a total of a whole bunch of these, so this is going to be a longer video. So feel free to, again, skip around, pause, and do whatever you need to do as you're going through this, but this will be a longer one. 8 different scenarios. Some will be similar, others will be a little bit different. Just kind of give you an idea of the different types of optimization questions you could see. So first up, we have a rancher wants to construct 2 identical rectangular corrals using 300 feet of fencing. So the idea is they're creating 2 rectangular corrals side by side. So we have a shape like this. So they're next to each other, so they're sharing that fencing there. So we share a side, saving up on fencing. So they want to know what dimensions should we use to construct a corral so that together we'll enclose the largest possible area. So we'll call these vertical components y's and we'll call these horizontal parts x's. So we can see we've got 2 equations. We have our area equation we're trying to maximize, which would be 2xy. Because the area would be the total rectangle area, and each individual rectangle is x by y, so it's 2xy. Obviously, we can't take a derivative yet because that's a 2-variable thing. We don't want to do a product, but we're not trying to deal with that scenario. But they do give us secondary information. We're using 300 feet of fencing. That's our perimeter. So our perimeter, 300, would have to equal 4x's and 3y's. So we're going to solve for one of the variables, either x or y, and then substitute into the area equation to create a single variable equation to take our derivative. It does not matter which one we solve for. I'm going to solve for y. So I'm going to go ahead and subtract the 4x over, and then divide by the 3. We get 100 minus 4/3 x equal to y. So it means our area equation is 2x times 100 minus 4/3 x, which means my equation, which has a function I'll write as a of x, is going to equal 200x minus 8/3 x squared. So we'll go ahead and take our derivative. So a prime would be 200 minus 16/3 x. We're going to set that equal to 0. And we're going to go ahead and solve this. So we would get 200 equals 16/3 x. Multiplying by 3 and then dividing by 16, we're going to get 37.5 x. When we fill that back in, y would equal 100 minus 4/3 of the 37.5, which is going to give us exactly 50. And they gave us units, so we got to say 50 feet for both of those. So what are the dimensions? So we're going to need the y components. The horizontals will be 50 feet, and each corral will have 37.5 feet, a total length of 75 feet when you put the 2 x's together. For the most part, we don't really need to, again, get into whether or not using a first derivative test or anything like that to confirm it's a maximum. We can kind of see that's exactly what's going to happen here. You can recognize from the very beginning, a of x is a negative quadratic. So we're doing a parabola like that, so we are creating a maximum point at our critical point there. So we don't necessarily need to worry about that. I will discuss when we get into some more interesting ones when we do need to get into first derivative test, second derivative test, the absolute max, absolute min, things like that, but we don't need it for this basic example. So that's a one. It's kind of a classic, creating rectangular corrals. Another one also, same farmer, but now we're putting a rectangular pig pen using 400 feet of fencing. It's not going to be two different corrals. We're building it next to an existing stone wall, so we're only using 3 sides of fencing. Again, doing everything we can to save on fencing. So our scenario looks kind of like this. We got our stone wall, and then we have a rectangular corral going through it. So we've got 2 Y pieces and an X piece. Now, depending on how you drew, you could have drew the stone wall vertically, so then you'd have 2 X pieces and a Y. So when they talk about the dimensions here, they're going to talk about the Y piece as what's perpendicular to the stone wall, and the X piece being parallel to the stone wall. Because obviously, if you draw it slightly differently or use different variables, they could have matched different things. So once again, we're trying to maximize the area, which in this case would just be X times Y. There's only one rectangle here. Again, 2 variables, so we do need a secondary equation. That's the perimeter, the 400 feet of fencing, created by X and 2Y. Now for this one, because X is by itself, we're going to go ahead and solve for X. So X would equal 400 minus 2Y. So we go ahead and fill that in for X. And we get, it's going to be A of Y now, because it's going to be equation of Y, is going to equal 400 minus 2y times y, which means A of y is 400y minus 2y squared. So again, it's an upside down parabola, so definitely there's going to be the vertex point is the maximum point here. We're trying to make the largest possible area. So our derivative A prime will be 400 minus 4y, set equal to 0, so 400 equals 4y. Y is 100 feet. And the next, when we fill that back in, is going to be 400 minus 2 times 100, which would be 200 feet. So the idea here is, y in this case was perpendicular to the wall, so it's going to be 100 feet, which is perpendicular to the wall, by 200 feet, which is parallel to the wall. If you're doing something like the AP, if this happened to be a free response question, which I would kind of doubt, this seems relatively straightforward enough, that would probably not be a free response level question, but let's just say it was. You drawing the diagram, you would not necessarily need to describe perpendicular and parallel to the wall like this. If it was a multiple-choice question, you would have to make sure you're identifying the correct spots for that, which this could be a multiple choice. That's more likely. I'm not saying it is, but at least that's a better chance. It's a straightforward enough question. Multiple choice is good for it. For your response, it doesn't seem to have the level of complexity that would be necessary for that. All right, so this next one here, so we got something more related back to our speed and stuff from Unit 4. Particle moves along the x-axis. Its position from the origin can be modeled by x of t, where x is in meters, t is in minutes. So we got 2 parts to this. What time during the interval 0 to 4 is the particle farthest to the left? So this is like an absolute maximum minimum scenario. So in this case, it's, I guess, more like absolute min, because left would be a negative direction. If one farthest to right, then it'd be like an absolute max. Either way, we need to find the critical point, and we need to consider the endpoints. So for part A, we're going to go ahead and take our derivative. So x prime at t is going to be a negative 2t squared plus 2t plus 12. We said that equal to 0. We want to solve for our critical point here. So we're going to go ahead and we're going to factor out the negative 2. Getting t squared minus t minus 6 equals 0. That factors as t minus 3 and t plus 2. So we would get t equals 3 and t equals negative 2 from this, but obviously negative 2 is invalid. Only the positive 3 would be necessary to worry about that. So we're going to go ahead and use that value right there and our endpoint, see which one is furthest to the left. Because this could be moving right here, could be moving left. We're not quite sure what's going on. So we want to find the position at 0, position at 3, and then position at 4. So we go ahead and plug in 0 into the original, negative 2/3, 0 cubed, plus 0 squared, plus 12 times 0 plus 1, and we obviously get, 1. All the other terms go away. Do the same thing with the 3, so negative 2/3 times 3 cubed, plus 3 squared, plus 12 times 3 plus 1, and we get 28. So obviously we were moving right. So we started off, looks like we were moving right, and then at 3, we're probably going to start going backwards. So odds are at 4, we're probably not going to go far enough back to account for getting further left than the 1, but let's just see what happens here. We fill in the 4 for each of these pieces, and yeah, we don't. We get 22.3 repeating. So we are farthest to the left here. At t equals 0, we are farthest to the left, because that's the leftmost value. All right, so in that same interval, now they're asking for part B, what is the maximum speed? So our maximum speed here is going to be based off, we want to find essentially the same thing, but based off acceleration. Because maximum speed, we're not looking for a relative max, we're looking for the highest actual value here. And keeping in mind, speed is the absolute value of velocity. So if we end up getting like a velocity of -10 and +5, the -10 is the faster speed because it's just simply moving to the left right there. So what I'm going to do is I'm just going to erase this work here that I did to find the farthest to the left. And we're going to do the same kind of analysis using our now acceleration. Because in order to find the maximum speed, we need the critical point of velocity, which means we need the second derivative. So we need the acceleration function. So we go ahead and find our second derivative, x double prime of t, would then be -4t plus 2. And we set that equal to 0. We get t to equal 1/2. So we're now going to go ahead and find our velocity, x prime at 0, x prime at 1/2, and x prime at 4. And see which one of these gives us the largest value of speed. So we would have -2 times 0 squared plus 2 times 0 plus 12. So clearly that's a 12. Nothing more going on there. -2 times 1/2 squared plus 2 times 1/2 plus 12. That's going to get us a 12.5. So that's obviously a little bit higher. And then they got the 4 here. So we're going to have -2 times 4 squared plus 2 times 4 plus 12. That is going to give us a -12. So that's essentially the same speed as at 0. Because even though it's negative, it's the same absolute value proportion. But this is obviously our highest speed. So what is the maximum speed? It's 12.5. This would be meters per minute because it's x is in meters, t is in minutes. So meters per minute. If they want the minimum speed, it would be a tie between the 0 and the 4, those two values, because those would be the lowest speeds there. Because again, negative doesn't matter for that. All right. So next up, all right, so now we're talking about point on the graph that's closest to the coordinate point 212, 2, 1/2. So if we're talking about closest, we're talking about distance, we need the distance formula. So your distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. So what we're going to do is we're going to fill in the, this 2 1/2 is going to fill in for the x1, y1. And then this is really y equals x squared, so we're going to fill that in for the y2. And we're going to say x2 is just simply the x. So our distance is going to be the square root of x minus 2 squared plus x squared minus 1/2 squared. So depending on how you want to handle this, you could leave it like this. I kind of want to distribute everything, FOIL it out, just because it's going to make the derivative eventually a little bit easier, in my view, to go through this. So when we FOIL this, we get x squared minus 4x plus 4. We get x to the 4th minus x squared plus 1/4. Again, all we're doing is just applying our perfect square foiling technique there. If you have to write it twice to FOIL it out properly, go right ahead. We're just recognizing that when it's in this format, x minus, when it's in the, what is it? It was a minus b squared, that became a squared minus 2ab plus b squared. That's all we're doing. So when we combine that, our distance would be the square root of x to the 4th. The x squareds would cancel each other, minus 4x and then plus 17/4, which we'll want to think of that as x to the 4th minus 4x plus 17/4 to the 1/2 power, because we now need to do a derivative. So if we think of this as d of x, so then we'd have d prime of x would be, well, this is our chain rule involving a radical. 1/2 goes in front, inside is left alone. Negative 1/2 power because we decrease by 1, and we multiply by the derivative of the inside, which is the whole reason why I went through and distributed the thing. It just made it a little bit easier to do that portion of it. Which when we take half of that and rewrite, we get 2x cubed minus 2 over the square root of x to the 4th minus 4x plus 17/4. So we want to solve this. So we're going to go ahead and solve the top. 2x cubed minus 2 equal to 0. That's going to give us x cubed equals 1, which means x equals 1. We should also, again, consider the inside portion of the radical. The x to the fourth minus 4x plus 17 fourths, set that equal to 0. That would require a calculator. And when we do that, we're going to go ahead and get an error message there. That's actually not solvable, so it's not actually really relevant. So the x equals 1 is where the location of the closest point is. And since y is equal to x squared, y would equal 1 squared, which is 1. So the closest point to this is a coordinate point 1, 1. All right, so typically when you're solving this involving like a distance formula, the denominator square root is not really going to be relevant. We're only going to really focus on the numerator there. And again, this is going to be the closest point. This does represent, again, a maximum spot. If we were to go through a first derivative test, testing out values, you would see that, again, you would go from positive to negative on either side of the 1. So that's why it's going to go off to it's going to go negative to positive on minimum value. So it's going to go, you're going to see, if you plug in, for example, 0.5, 2 times 0.5 cubed minus 2 is giving you a negative value. Whereas you plug in 2 times 2 cubed minus 2 gives you a positive value. So that's why I get negative to positive, decreasing, increasing, minimum points. All right, along those same lines, we now got a rectangle formed inside, this is nice, inside a quadratic, y equals 20 minus x squared. So if we look at that graph, something like that right here, we have the y equals 20 minus x squared, looks kind of like this. It's going to peak here at 20. It's going to hit here and here at, it's going to be 2 root 5, positive and negative. But what we really are doing is we're fitting a rectangle inside here like this. That's the rectangle that's being fit inside there. And you notice, because it's all perfectly symmetrical, these are both x's, and that's obviously then a y. So those are coordinate point xy right here. That's fitting exactly on our shape. And that's important because the area of our rectangle is once again based off 2xy, because there's 2x down on the bottom and 1y going vertically, so that's why it's 2xy. And here they give us y equals 20 minus x squared. That's going to replace the y here to make it a function of x, so we can actually take a derivative and solve this out. So a of x would equal 40x minus 2x cubed. We go ahead and take our derivative. We get 40 minus 6x squared. Now we go ahead and set that equal to 0. So that would give us 6x squared equals 40. X squared would equal 20 over 3. And the square root of that, well, we'd get positive and negative. Obviously, when it's negative, that accounts for on the negative side here. Positive accounts for on the positive side. So either way, that's our value of x. It's the square root of 20 over 3. We're going to leave it like that in the exact form. Y would be 20 minus this squared, which obviously, since we square root, that would cancel it. Leaving it to be 20 thirds, we can make this as 60 thirds. So the y value is at 40 thirds. So the dimensions of the rectangle, you would have, they didn't give us units, so the x value would be root 20 over 3. That would essentially represent half of the length, if you consider that part the length there. So our full length of our rectangle would be 2 times the square root of 20 over 3. And obviously we'd have 40 over 3 for this portion. If they wanted us to kind of simplify that radical a bit more, we could. We're going to just leave it in that radical format like that. We're not going to rationalize. All right, so here in this next example, we've got a swimmer. They are 500 meters from the closest point to a straight shoreline. So if we have our swimmer right here, we'll call him S. This is 500 meters to the shore. There's our shore. She needs to reach her house located 2,000 meters down the shore from the closest point. So this would be down here. So there's our house. This would be 2,000 meters. If she swims at 0.5 meters per second, runs at 4 meters per second, how far from her house should she come ashore to drive her house in the shortest time? Because obviously what you could do is she could swim straight to the shore, those 500 meters, and then run the 2,000 meters. Or she could just swim the entire time on the diagonal from the shore, from where she is to the house, and that whole time, and see that there. Both those scenarios are generally not the most ideal scenario. Even if you are running significantly faster than you're swimming, you generally don't want to run the whole distance as much as possible. In general, what you're going to want to do is you're going to want to swim at like a diagonal and hit the shore somewhere like here. wherever that happens to be. We'll call that value, that particular distance, we'll say it's x from there, so this part is 2,000 minus x. So you're going to swim a little bit and then run a little bit. You're not going to swim the full maximum distance of swimming, which is the swimmer to the house. You're also not going to run the maximum distance, the whole shoreline, the 2,000. You're going to do a little bit of both. And we're going to use this information now to, again, we're trying to figure out a minimum time. So time is always going to be based on, we know that distance equals rate times time. So time is going to equal distance divided by rate. And we're going to have to set up two different time equations, the time for swimming and the time for running. So it means we're going to have to figure out the distance equation for our swimming distance. We can obviously, our running distance is 2,000 minus whatever x is. So this swimming distance, I'll call y, is going to be based off the right triangle involving 500 and the x. So we know that x squared plus 500 squared is going to equal the y squared. So we take the square root of all that. So y is going to equal the square root of x squared plus 500 squared. I'm not going to square out the 500. It's not relevant yet. When we get to solving, we'll need to do that, but we're going to kind of leave it in that squared format right there. So when we're solving this, our total time is going to be the time for the swimming portion, which would be the distance of swimming, square root of x squared plus 500 squared, over its rate, which is 0.5, plus then the time for the running portion, which its distance is 2,000 minus x over its rate, which is 4. So those are our two pieces of the puzzle. We're going to go ahead and recognize if we're dividing by 2, that means we're really dividing by 0.5 is really multiplying by 2. So it's 2 times x squared plus 500 squared to the 1/2 power. This would be 500 minus a quarter x. And now we can go ahead and take our derivative. So t of x prime for our derivative here. 2 times 1/2 is a 1, so that leaves it as x squared plus 500 squared to the negative 1/2 times 2x. The 500 disappears here. Minus a quarter x means minus a quarter, and we set that equal to 0. So ultimately, this equation right here is not really going to be nicely solvable. We're not going to go ahead and try and solve this one algebraically. You're going to go ahead and just take a calculator and you're going to graph this. So what you're going to do is in your calculator, it might make your life a little bit easier to write as 2x divided by the square root of x squared plus 500 squared minus a quarter. And again, you're going to graph and see where it crossed the x-axis. That's the beauty of it setting it equal to 0, because you can find x-intercepts. And you're going to find this x-intercept will occur when x is going to be 62.994. This would be meters then. So ultimately what's going to happen is you're going to swim. So the total distance you're actually going to run, which obviously you're going to run a lot more than you're swimming, because again, rate-wise, 4 versus 0.5. You're going to run a total of 2,000 minus that 0.994. You're going to get 1,937.06 meters. That's how much you're running. So that's how far from the house you should be. Because you want to find essentially what the 2,000 minus x portion is going to be. If they want us to find how much, how far this person is swimming, we would then obviously substitute that value into the y equals equation, solve for the y value. But yeah, so that's how far offshore we're going to go. So obviously we're going to spend significantly more time running than swimming, but as I said earlier, I'm kind of rambling a little bit. It makes sense. You're swimming at a rate, you're running at a rate that's 8 times faster than you're swimming. So there should be a significant more of a portion where you're going to run versus you're going to swim. All right, so in this next example, we're talking about creating a border around a movie poster. So we're doing a rectangle around a rectangle. So we have a larger rectangle, including the border. And on the inside rectangle, that's our 98 centimeters squared. We're going to see the dimensions are 2 centimeters on top, 2 centimeters on the bottom, 1 centimeter left side and right side. Our original dimensions, we'll call them x and y. I'm going to do them in orange so we can kind of see them a little better. So obviously horizontal, I'm going to use x. Vertical uses the y, which means the overall movie poster would be x plus 2 and y plus 4 for those dimensions. Now, the actual poster itself, without the border dimensions, will just be x times y equals 98. Whereas the area of the full shape with the border dimensions would be x plus 2 times y plus 4. So we go ahead and distribute all that, FOIL that loveliness. We get xy plus 4x plus 2y plus 8. We can fill in xy is 98, and then we need to solve for one of the variables. Either x or y to replace the x for the 4x or the y for the 2y. As always, our secondary and our primary equations. Let's go ahead and solve for x. So let's say x equals 98 divided by y, which I'll want to think of that really because the derivative is 98y to the negative first. So this becomes 4 times 98y to the negative first. 2y is left alone, and plus 8. This gives us a full area function, a of y, as a 106 plus a 392y to the negative first plus 2y. And now we take our derivative. 106 goes away. We get negative 392y to the negative second plus 2. And as always, we're finding critical points, so it's set equal to 0. Now, if we were to subtract the 2 and then also rewrite this as a positive exponents, we get this right here. So the negatives essentially will cancel each other out. Multiplying y squared gives us 392 equals 2y squared. So 196 equals y squared, therefore, 14 is equal to y. Technically negative 14 algebraically, but we can't have a negative dimension. Y is 14, therefore x is 98 over 14, which is 7. So the overall dimensions, we would fill in y is 14, so 4 plus 14 would give us 18 centimeters. 7 plus 2 would give us 9 centimeters, so this thing would be a 9 centimeter by 18 centimeter poster, where the 9 is the horizontal and the 18 is the vertical. Okay. So be careful with that kind of stuff. Be careful. Again, we would have gotten the same answer if we had solved out for y instead of x. Obviously, we'd just get an a of x equation instead there. Just make sure you're being careful with your power rule there. That's why we're writing instead of 98 over y as 98y to the negative first. We don't need quotient rules if we have a numerator of a number instead of a variable. Just watch out with where you're putting the 98. Common mistake is to think that the x plus 2 times the y plus 4, that equals 98, and the xy is what we're trying to optimize. Again, they told us the poster is 98, and we're putting a border around it. So the inside is 98, the part around it is the unknown. If they told us the area of the poster is unknown, but we have a total of, again, 98 square centimeters paper with a border and then a poster, how big can we make the poster? Then the xy is the unknown, and the area is based on the 98. So just, again, as always, I know it's math, but we got to pay attention to context clues, so your English skills, your ability to read and comprehend what they're saying, it's going to come into play a lot. All right, you listened to me for 7 examples. Let's do one more, and then you're done listening to me for this. So we're creating an open-top box with a piece of cardboard that is 14 by 30 inches. So we have a 2-dimensional cardboard box. We want a cardboard piece of cardboard, and we're going to make it into a 3-dimensional shape by cutting out squares in the corners so we can fold it upward. So the idea is this is the original piece of cardboard. Let's make this part the 30 inches, this part the 14 inches. It's not really going to matter. We're cutting out corners here, here, and here so that we can fold it upwards. For those of you in class, if you're a little unsure what's going on here, I will just simply show you what that looks like. I'll physically take a piece of paper, cut out some corners so you can see me folding and creating a 3-dimensional shape. For everyone else, again, if you just take your own piece of paper, again, cut out the corners, and then fold along where those corners were, you'll create a box. Not a very strong box if it's a piece of paper, but you can still create a box. Now, how big those corners are, we have no idea. So those are x's. Now, we're trying to maximize the volume, so we need a volume equation here. So we need to recognize that this box, the x is going to be the height, because volume is length, width, and height. The height represents the x, because that's what's folding upwards. The length and the width is based off the 30 and the 14, but we're taking away x's from both of them. In fact, the length, you're taking 2 x's from it, so it's 30 minus 2x. And then the width, you're taking 2 x's from the 14, so it's 14 minus 2x. So everything is based on this x that we're taking away from the corners. So our volume, we would have 30 minus 2x times 14 minus 2x times x. So we're going to fold all this together, multiply, create a nice equation. So v of x is going to be, so our 30 Times our 14 is going to be 420. And then minus 60x minus 28x plus 4x squared. The whole thing is going to multiply with x, which is going to give us 420x. 60 and 28 make 88, so it's going to make a negative 88x squared. And then plus 4x cubed. So we go ahead and take our derivative, because we're trying to find our critical points. Dimension-wise, we know that obviously x has to be bigger than 0. We need to be able to cut something out. It cannot be larger than 7. Where did I get 7 from? Well, that's based off the smaller dimension, the width right here. 14 minus 2x equals 0 occurs when x is 7. So if x is bigger than 7, this is not possible then. Because obviously then we would cut out the square that would equal the entire width there. We don't no longer have a, foldable piece. So it's got to be somewhere in between 0 and 7 to be an actual size that will work. So we take our derivative, we get 420 minus 176x plus a 12x squared. Now it's creating a quadratic. Depending upon the question itself, this one is factorable. If you're not sure and you are allowed to use a calculator, then obviously you can just go right to the calculator, graph this, see where it crossed the x-axis. A negative value, a value bigger than 7, all of that would not be relevant. If it was a non-calculator type of question with AP or with your teacher, whatever, that implies this is factorable. So let's assume that. We're going to go ahead and recognize we can factor out a 4 for every single one of these terms, giving us 3x squared minus 44x plus 105. This part might be a little more interesting, but that does factor. Oddly enough, it does. We're going to create an x minus 3 and then a negative, let's see, so that's 9. I want that to be 35. Turns out that works because that gives you the positive 105, you do 35 times 3. And when you FOIL it, you get negative 9, negative 35, which is negative 45. So this first one gives us 3x equals 35, which x is then 35 over 3, which is 11.6 repeating. Too large, though. It had to be less than 7. That one gives us x equals 3, so that's great. So our corners are going to be 3 inches by 3 inches. So if we cut out a 3-inch corner from each of those corners there, it's going to fold up and create a maximum value for this particular type of box. All right, so that was obviously a lot going on there. I had to actually piece this together in multiple parts for various editing reasons, so I'm not quite sure exactly how long it is off the top of my head. I'm sure it's over 20 minutes, maybe approaching 30. We'll see. Either way, well worth it, though, I think. There are plenty of examples here for you to walk yourself through, try on your own, see how I did it, all that stuff, and apply it to everything else. This obviously does not encompass every single possible optimization scenario. That's just not practical. There's no way for us to truly go through every single possible scenario here, but there are plenty that were discussed here in this particular video. That's it for Unit 5. So that's it really with derivatives in terms of new information regarding something that could possibly show up on the AP Calculus test. There are more things to talk about with derivatives in terms of things for like a college level class. But again, in terms of the AP or for a high school level class, this is it for the derivatives. Going forward with Unit 6, we're going to talk about the idea of the antiderivative and introduce the idea of the integral and working with things like that. And then we'll get into solving differential equations Unit 7 and applying integrals in Unit 8. As always, appreciate you watching, and I'll see you next time.